The modern industrial world is built on the foundation of trial and error. Whether we are talking about the steel in a skyscraper, the lithium in a battery, or the fertilizer that feeds half the planet, every material we use was discovered through a slow, expensive process of physical experimentation. We mix chemicals, heat them up, and see if they explode or if they hold a charge. But we are about to move from the era of discovery to the era of architecture. We are entering the age of quantum material discovery, where we will no longer have to guess what a material will do. We will simply simulate its atoms in a quantum environment and build the future from the subatomic level up. To understand why this is a revolutionary leap, you have to look at the limits of classical chemistry. Every molecule is held together by the movement and interaction of electrons. Electrons are quantum particles. They don't just sit in one spot, they exist in complex clouds of probability. When you try to simulate even a simple molecule on a classical supercomputer, the math becomes overwhelming. This is known as the many-body problem. Because every electron interacts with every other electron, the complexity grows exponentially. To perfectly simulate a single molecule of caffeine, a classical computer would need a memory bank larger than the planet. Because we cannot simulate the quantum reality of atoms, we have to use approximations like density functional theory. We make educated guesses. This is why it still takes 10 years and billions of dollars to bring a new drug to market or to develop a slightly more efficient solar panel. We are essentially trying to paint a masterpiece while wearing a blindfold. Quantum computers remove the blindfold. Because a quantum computer operates on the same laws of physics as the atoms it is trying to simulate, it doesn't have to approximate the math. It is the math. A quantum processor can map the electron folding of a complex protein or the magnetic properties of a new alloy with absolute accuracy. This isn't just a faster way to do chemistry. It is a way to do chemistry that was previously impossible. We are talking about the ability to build materials that have properties we've only ever dreamed of. Substances that are as light as plastic but stronger than titanium. Or membranes that can filter salt out of seawater with almost zero energy through precise nanopore engineering. One of the most high-stakes goals in this field is the discovery of a room-temperature superconductor. Currently, we lose about 10% of all electricity generated simply because of the resistance in our copper wires. Electricity is lost as heat, which is why your laptop gets hot and why power lines hum. Superconductors have zero resistance, but they currently only work at temperatures colder than deep space. If we can use quantum computers to architect a material that superconducts at room temperature and ambient pressure, it would be the most significant invention since the steam engine. We could transmit power from a solar farm in the Sahara to a city in Europe with zero loss. We could build hyperloop trains that levitate on permanent magnets and fusion reactors that actually produce more energy than they consume. We haven't found this material yet because the search space of chemical combinations is too large for classical computers to explore. Quantum computers will turn that search from a needle in the haystack problem into a guided precision engineering project. Beyond energy, this transition will fundamentally reshape how we interact with the environment through carbon and nitrogen management. Currently, about 2% of the world's total energy consumption is used for a single process, the Haber-Bosch process, which creates the ammonia for the fertilizer that keeps the global population alive. This process requires massive heat and pressure because we aren't very good at breaking nitrogen bonds. However, a tiny bacteria in the roots of plants does the same thing at room temperature using a specific enzyme called nitrogenase. We've never been able to replicate this because we can't simulate the quantum mechanics of that enzyme's active site. A quantum computer could map that process in a week. If we could replicate that bacteria's efficiency on an industrial scale, we could slash global energy use and carbon emissions overnight. We are also looking at the creation of carbon-negative materials. Imagine a concrete that doesn't release CO2 during production, but instead absorbs it from the atmosphere as it cures. Or a new class of catalysts that can turn atmospheric carbon directly into high-grade carbon fiber for construction. These are not science fiction. They are simply specific arrangements of atoms that we haven't been able to calculate yet. This is the shift from finding to designing. In the late 2020s and early 2030s, the most valuable mines in the world won't be physical holes in the ground in South America or Africa. They will be quantum algorithms. The nations and companies that can simulate the next generation of solid-state batteries, carbon capture membranes, and high-strength alloys will control the global economy. We are moving toward a post-scarcity material world, where the only limit is our ability to imagine the structure of an atom. The age of building with whatever we could find in the earth is ending. The age of building exactly what we need is just beginning. If you want to see how we are moving from the laboratory to the field with these new architectures, make sure you stay with us. The blueprint for the future is being written in the quantum realm.